Hi students, have a nice day. In this section we are going to discuss about the aromaticity and physical and chemical properties of aromatic hydrocarbons. Benzene was considered as a parent aromatic compound. Now, this concept is applied to all the ring systems, whether it is benzene or benzoid or non-benzoid. Okay, some aromatic compounds are benzene or benzoid system, some others are not benzoids. Okay, several theories explain the aromaticity. Sector theory, Huckel's rule, or it is known as 4n plus 2 rule. And the very important theory is Huckel rule or 4n plus 2 rule. So in our syllabus, Huckel rule is given. Okay, Huckel's explained the aromaticity of benzene or ring systems. The important features of Huckel rule or important postulates of Huckel rules are: the very first one is the compound must be cyclic and planar. The compound must be cyclic and planar. And the second point is complete delocalization of pi electron through the ring or in the ring. Okay, the complete delocalization. What is delocalization? The shifting of pi electrons. Conjugation. So, complete delocalization or conjugation of pi electrons in the ring. And the third important feature is the cyclic system, the compound or the ring should contains 4n plus 2 pi electrons. Okay, the presence of 4n plus 2 pi electron in the ring. And where n is equal to 0, 1, 2, 3, etc. Okay, let's discuss some examples. Okay, Huckel's rule. Huckel rule. It is also known as 4n plus 2 rule. 4n plus 2 rule. First important point is the compound is cyclic and planar. The compound should be planar. It's very important. And the second point is delocalization of pi electrons. Delocalization of pi electron in the ring. And the third important point is 4n plus 2 pi electrons. 4n plus 2 pi electron in the ring. And where n is equal to, okay, where n is equal to 0, 1, 2, 3, etc. If n is equal to 0, apply into this formula 4 into 0 plus 2. That is equal to 2 pi electrons. Okay, 2 pi electrons. Where n is equal to 1, 4 into 1 plus 2. That is 4 into 1, 4 plus 2, 6 pi electrons in the ring. And if n is equal to 2, 4 into 2 plus 2, 4 into 2, 8, 8 plus 2, 10 pi electrons in the ring. And if n is equal to 3, 4 into 3 plus 2, that is 14 pi electrons. Okay. So very important and simple concept. Those molecules behaves aromatically or the molecule have characteristic smell. The following features for that molecule: cyclic and planar. The compound should be cyclic and planar. Second one is delocalization of pi electron in the ring. Okay, and the third one is the presence of 4n plus 2 pi electrons, or the molecule should contain 4n plus 2 pi electron in the ring. Okay, and where n is equal to 0, 1, 2, 3, etc. And here we put the values of n, we get different numbers of pi electrons. 2 pi electrons, and these 2 pi electrons in the ring as well as complete delocalization. The compound is aromatic. Then 6 pi electrons. Okay, 10 pi electrons, 14 pi electrons. Let's discuss some examples. Okay, let's discuss some example. So important you study this. Next we discuss some examples. Okay, the first one is benzene. Benzene. Benzene is cyclic and planar. Okay, sp2 hybridization. sp2 hybridization molecule is planar, trigonal planar. And resonance is possible. Okay, or it has the structure like this. So delocalization of electron is possible, and the number of pi electrons, 1 pi bond, 2 pi bond, 3 pi bond. So one bond is considers of mutual sharing of 2 electrons. So 1 pi bond, 2 electrons, so that is 3 pi bond, 6 pi electrons. 3 pi bond, 6 pi electrons. So benzene is aromatic. Benzene is aromatic. And the another one is naphthalene. First of all, we consider the benzoids. Okay, this is naphthalene. 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 Naphthalene is containing, okay, this molecule contains 10 pi electrons. 10 pi electrons. 1, 2, 3, 4, 5. Okay, there are 5 pi bonds. So 5 into 2, 10 pi electrons. Also it has an resonance structure. A compound which contains 10 electrons and it has resonance structure. Okay, this one shifted to here, come to here, come to here. Similarly, in the next ring also we can draw the resonance structure. So two resonance or delocalization of electrons and 4n plus 2 electrons. Another is anthracene. Anthracene. 3 benzene rings are joined. Okay, 1, 2, 3, then 2 pi bonds, 2 pi bonds. This is anthracene. Anthracene. Okay, this compound contains 14 pi electrons, and delocalization is also possible. Okay, let's count 1, 2, 3, 4, 5, 6, 7. 7 pi bonds. Okay, 7 pi bonds, so 7 into 2, 14 pi electrons. Aromatic. Okay, aromatic. This also aromatic. And another is phenandrine. Okay, phenandrine. This is a phenandrine. Okay, phenandrine. So phenandrine also contains 14 electrons, 14 pi electrons. So phenandrine also aromatic. Okay, I think you understand the concept. The compound should be cyclic and planar. Delocalization of pi electrons. Okay, delocalization of pi electrons, and the compound or molecule contains 4n plus 2 pi electron in the ring. Okay, 4n plus 2 pi electron in the ring. So that's about the benzoids. Okay, aromaticity of benzoids. Then let's discuss some other example of cyclic ions or non-benzoid compounds. Okay, non-benzoid compounds. The first one is furan. Okay, the first compound is furan. This is a furan. Okay, furan. Then the compound is cyclic. Then resonance also possible. If this electron shifted to this side, this come here, this come here. Okay, so resonance also possible, and it contains 6 pi electrons. In the ring, 1, 2, 3, 4, 5, 6. Okay, so the molecule furan contains 6 pi electron. It is aromatic. And another one is cyclopentadienyl anion. Cyclopentadienyl anion. A minus charge, that is a pair of electron. Okay, the bond comes here, then move to, then like that, the resonance is possible. Okay, resonance is possible. So this cyclopentadienyl anion. Dienyl anion is aromatic. The next is cycloheptatrienyl cation. Okay, cyclohepta, 6, not 6, 7 carbon atom in the ring. Cycloheptatrienyl cation. Cycloheptatrienyl cation. Okay, 1, 2, 3. 6 pi electrons in the, here also 6 pi electrons. 6 pi electrons in the ring, and the resonance is possible. If the bond shifted to here, plus point comes here, then again plus point, bond is shifted, plus point. So the positive charge resonating through the ring. Okay, resonating through the ring, and the compound is containing 4n plus 2 pi electron, that is 6 pi electrons. But you remember that cyclopentadienyl cation and cycloheptatrienyl anion, they are non-aromatic. Okay, we will discuss what happens in that. So these are non-benzoid system. Okay, and what happens when we cyclopropynyl cation? Okay, cyclopropynyl cation. 2 pi electrons. 2 pi electrons. And this molecule is aromatic. Why? It is a cyclic compound. Okay, cyclic compound and 2 pi electrons, resonance is possible. If the bond shifted to here, plus point comes here. Okay, plus charge come here. If the bond shifted to this side, plus charge is on the that carbon atom. Okay, are you clear? Yes. So these are the non-benzoid system. Then let's discuss some non-aromatic compounds. Okay, non-aromatic compounds. In the case of non-aromatic compounds, the very first example is cyclopropenyl anion. Okay, cyclopropenyl anion, minus charge. So 4 pi electrons in the ring. 4 pi electrons in the ring. So that's why it is non-aromatic. Non-aromatic. Okay, 4 and plus 2 pi electrons. That's very important. 4 and plus 2 pi electrons. The number of 4 and plus 2 pi electrons already we determined 2, 6, 10, 14. Okay, 2, then plus 4, it is 6, 6 plus 4, 10, 10 plus 4, 14. The number is like that. So here 1, 2, 3, 4. 4 pi electrons non-aromatic. Okay, but cyclopropenyl cation is aromatic. And another one, cyclopentadienyl cation. Anion is aromatic. Anion is aromatic. And this molecule is cyclic, planar, delocalization is possible, but the number of pi electron is 4 pi electrons. 4 pi electrons. Okay. Cyclopentadienyl anion is aromatic because cyclic, then planar, delocalization is possible, and 6 pi electrons in the ring. 6 pi electrons in the ring. But here, cyclic and planar, delocalization is possible, and 4 and plus 2 electron doesn't satisfy. The molecule is non-aromatic. Okay, the molecule is non-aromatic. Another one. Okay, cyclohexadienyl compound. Cyclohexadiene. Cyclic, no conjugation. Okay, complete delocalization is restricted, and also it contains 4 pi electrons. It is non-aromatic. Okay, cyclohexadiene is a non-aromatic compound. Okay, similarly you can determine more compounds which contains 4 and plus 2 electron, and it doesn't contain 4 and plus 2 pi electrons. So aromatic theory is a very important theory in the board exam as well as competitive examination. Yes, next we move to the properties of aromatic compounds. First of all, physical properties. Aromatic compounds are non-polar compounds. Usually they are colorless liquids or solids. Okay. First point is they are non-polar, physical properties. Physical properties. First one is they are non-polar. Non-polar compounds. Second one is usually they are colorless liquids. Colorless liquids or solids. And they have characteristic smell. They have characteristics aroma. Okay, benzene, kerosene-like smell. Okay, then naphthalene, you know that naphthalene, it is used as a mothball. It is used in the toilet or which is kept in our shelves or almirah for the property of repelling ants and moths. Okay, and repelling property. Moth or ants are repelled by the characteristic smell. That's why they are used as mothballs. Okay. Naphthalene has characteristic smell. And another important point is they are lighter than water. Density is less, lighter than water. And the next is they are highly inflammable. Usually they are highly inflammable and they burn in the air with a sooty flame. Okay, sooty flame. Sooty flame. Then density, lighter than water. Lighter than water. Characteristics, aroma. Characteristic smell. So all these are the important physical properties of aromatic compounds. Next is chemical properties. Aromatic hydrocarbons characterized by electrophilic substitution. Okay, aromatic hydrocarbons characterized by electrophilic substitution. And under special condition they undergo addition reaction and oxidation. Only in this special conditions. Okay. So electrophilic substitution are important reactions in the aromatic compounds. Let's discuss some electrophilic substitution reaction. They are nitration, halogenation, sulfonation, and Friedel-Crafts reaction. Okay, Friedel-Crafts reaction. So main reactions are these: nitration, halogenation, sulfonation, and Friedel-Crafts reaction. Okay, let's discuss one by one. Chemical properties, electrophilic substitution. Let's discuss one by one. Chemical properties. Electrophilic substitution. Electrophilic substitution. One is nitration. Nitration. Benzene is heated with, okay, you put either alternative double bond or a circle or dotted structure as you like, plus concentrated HNO3. Con HNO3. Concentrated sulfuric acid as a catalyst. 323 to 333 Kelvin. We get nitrobenzene. Or okay, you know that 6 carbon atoms are identical. Or you can write like this. Both are same. Nitrobenzene, nitrobenzene. Okay. Only one substituent. It can be given at any carbon atom because 6 carbon atoms are identical. So this is nitration. Nitration of benzene. Remember that concentrated nitric acid and concentrated sulfuric acid is taken. And this is called a nitrating mixture. Concentrated HNO3 plus concentrated sulfuric acid is called a nitrating mixture. Nitrating mixture. Remember that. Second one is halogenation. Halogenation. Benzene is treated with Lewis acids. Okay, Lewis acids such as anhydrous AlCl3, FeCl3, FeBr3, etc. We will get halo derivatives. Okay, the Lewis acids such as anhydrous AlCl3, FeCl3, FeBr3, etc. We will get halo derivative. Let's take one example. Benzene. Benzene is treated with chlorine in the presence of anhydrous AlCl3. Anhydrous AlCl3, we get chlorobenzene. Okay, also you take the catalyst FeCl3. FeCl3. Okay, anhydrous AlCl3 or FeCl3, we get the same product. Okay, chlorobenzene. Chlorobenzene is the product. Repeat this. Benzene plus chlorine. And for bromination, what we take? Benzene plus Br2 FeBr3. Okay, FeBr3. We get bromobenzene. Fluorination and iodination is different method. Okay, fluorination and iodination is in a different methods. You will learn in the +2 classes. Okay, so that's about the nitration and halogenation. Next is sulfonation. So concentrated sulfuric acid plus SO3 gas. It is called oleum or fuming sulfuric acid. Concentrated sulfuric acid with a dissolved SO3 called a fuming sulfuric acid. Con H2SO4 plus SO3 gas, that will give H2S2O7. It is called a oleum or fuming sulfuric acid. When benzene is heated with H2 concentrated H2SO4, con H2SO4 plus SO3 gas, or you can take H2S2O7, we get benzene sulfonic acid, SO3H. Heat, we get benzene sulfonic acid. A very important reaction. Sulfonation. Okay, sulfonation of benzene. Say electrophilic substitution. Next one is Friedel-Crafts reaction. The last one is Friedel-Crafts reaction. Okay, in Friedel-Crafts reaction, two type of Friedel-Crafts reaction. One is Friedel-Crafts alkylation and the other is Friedel-Crafts acylation. Okay, first one is Friedel-Crafts alkylation and the second one is Friedel-Crafts acylation. The catalyst is anhydrous AlCl3. Okay, let's discuss Friedel-Crafts reaction. Friedel-Crafts reaction. Okay, Friedel-Crafts reaction. First one, A. That is first one. Friedel-Crafts okay, it is C. Crafts. Alkylation. Benzene plus alkyl halide. Benzene and alkyl halide. The catalyst is anhydrous AlCl3. Catalyst is anhydrous AlCl3. We get toluene as a major product. Okay, toluene plus HCl. Byproducts are usually denoted in the organic reaction. When you take ethyl chloride, what happens? CH3, CH2, Cl. What is the product? That is ethyl benzene. When you take methyl chloride, you get toluene or methyl benzene. When you take CH3, CH2 ethyl group, you will get ethyl benzene. So generally we can write that the R group, Rx, that gives, okay, anhydrous AlCl3, that gives alkyl benzene. Okay, so alkyl benzenes are obtained when alkyl halide is treated with, okay, benzene and alkyl halide treated with the anhydrous AlCl3. That is alkylation, alkyl group substitution, alkylation. And the next is acylation. Okay, Friedel-Crafts acylation. Very simple reactions. All the reaction you should learn by writing, otherwise you forgot it. Okay, Friedel-Crafts acylation. Acyl group means CH3 C double bond O group is attached. Acyl group. So here benzene plus CH3 C double bond O Cl in the presence of anhydrous AlCl3. Anhydrous AlCl3, acetophenone is obtained. Acetophenone. Okay, acetophenone is obtained. Also it can be done with acetic anhydride. Okay, acetic anhydride also used. The catalyst is anhydrous AlCl3. Just heat, we get the same compound, acetophenone. Okay, so two reagents usually we use. One is acetyl chloride and acetic anhydride. This is acetyl chloride and acid chloride. This is acetic anhydride. Acetic anhydride. Also an acid derivative. Okay, next when we treat benzene and 6 moles of chlorine in the presence of anhydrous AlCl3 and dark. Okay, benzene, 6 moles of chlorine, the catalyst is anhydrous AlCl3 and dark. Okay, dark and cold condition, we get hexachlorobenzene. The 6 hydrogen atoms are substituted. 6 hydrogen atoms in the benzene are substituted. It is called hexachlorobenzene. Hexachlorobenzene. So these are some important electrophilic substitution. The mechanism we will discuss in the next section. Okay, so we will see the mechanism and the other important orientation factor in the next section. Thank you.